the spectra that's linked with a diatomic molecule. And when we have a diatomic molecule, we have two atoms, and we assume that these two atoms are at some equilibrium distance with respect to each other. And now talking about this dual, uh, this molecule which has two atoms in it, which is the simplest with respect to other molecules, we can have we can have we can have two types of motions that can be uh, that can be that can be considered. The very first thing is that this molecule as a whole can rotate, and it can rotate, and the rotation can be along the axis of the two atoms, and the rotation can be along the axis that's perpendicular to the separation between the two atoms. So this rotation that we're talking about here is this rotation will give rise to uh, it can interact with the electromagnetic radiation depending on the molecule under consideration. If the molecule has the permanent electric dipole moment, uh, then certainly the electromagnetic radiation will interact with it, and we will have the absorption spectra, and we will have the emission spectra. But at the same time, if the net dipole moment of the molecule, I mean, in case of hydrogen, uh, hydrogen molecule, nitrogen molecule, we will not be able to see this what we call as a rotational spectra, because the because this kind of diatomic molecule uh, does not have the electric dipole moment, and so electromagnetic interaction is not going to interact with this molecule. But when we have a diatomic molecule like hydrogen chloride, where we have the net electric dipole of this molecule, there, we will certainly have the rotational spectra. Now, depending on what kind of assumptions are taken in discussing the rotational spectra of this molecule. Now, at the same time, this molecule can have vibrational spectra. I mean, when we talk about the vibrational spectra, what we have is, if we have a diatomic molecule, we have the nuclei of the two atoms, and we have the electron clouds. So there are different interactions involved in this molecule. We can have the repulsive forces between the nuclei of the molecule, and we can have the repulsive forces between the electron cloud of the two atoms that are under consideration. And at the same time, we will have the attractive force between the nuclei and the electron cloud. So, so what we will have here is that 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 we will have certain considerations, and these considerations will be taken care of in discussing. Now let's talk about vibrating diatomic molecule. And what we have here is, we have uh, when we have two atoms, and when the two atoms combine to form a stable covalent bond, uh, we have a molecule. Now, say for example, potassium chloride, KCl, or hydrogen chloride. They may be said to do so because of some internal electronic rearrangement between the two atoms. And what is important to discuss here is the detailed. We are not actually in a state to discuss uh, the detailed mechanism of this bond formation between these atoms. But what is important here is that we would like to simply look on the phenomenon of balancing forces. At the same time, on the other hand, there is, there is repulsion between the positively charged uh, nucleuses, and both the nucleuses, what they do is they repel, because the two atoms, they have nuclei, and these nucleuses have same charge, so there will be repulsion between these two nucleuses. And of course, there is electron cloud for both of these nucleuses, and within that electron cloud there will be the repulsion between the electrons. And on the other hand, there is an attraction. There is an attraction between the nucleus of one atom and the electrons of the other, and vice versa. The two atoms settle at a mean internuclear distance. So when we say that there is an equilibrium, when we assume an equilibrium, so there's a settlement, there's an overall uh, balancing of the forces. Now the atoms settle at a mean internuclear distances, such that these forces are just balanced, and the total energy of the whole system uh, is uh, is minimum. It carries a minima. And talking about the atoms, and if we try to take these two atoms, say this is atom one and this is atom two, if we try to bring them close together, what's going to happen is they will exert a repulsive force, and this repulsive force will rapidly increase as we will try to bring down the two nucleuses close to each other. So when we will try to pull them, so the first case was to when we will try to bring them close. Now, if we try to get them away from each other, from their equilibrium position, uh, so while pulling them apart, there has to have a resistance by the attractive force. Uh, so any kind of distortion that we would like to execute on this molecule, whether we try to compress the molecule, or we try to expand this molecule, we have to add the energy to disturb the equilibrium of this molecule. Now, if we take an example of this hydrogen chloride. And what is important here is that we understand that the mass of chlorine is very large in comparison to the mass of hydrogen. And we can treat this chlorine atom can be treated to be at rest, and we can think of a hydrogen atom as as having a vibrational motion. So, so what am I trying to tell here is that uh, what we assume here is, if we take an example of this hydrogen chloride molecule, uh, at the minimum energy, the internuclear distance that is between chlorine and this hydrogen atom, this distance it's referred as basically equilibrium distance. Equilibrium distance. And let us assume that this equilibrium distance is R eq. Or, or to speak it in more precise way, is that this compression, whether we have the compression or we have the extension of a bond, and this compression and extension of the bond may be linked to the behavior of something like, suppose this is chlorine, and something like a spring, and we may extend this problem for this molecule analogous to a spring, and by assuming that the bond is behaving exactly like a spring, and it obeys Hooke's law. and and for that we can have a force, what we call as a restoring force, and we can write down that as minus times k is the spring constant, times r minus r equilibrium. So this k is a force constant. We may also call it spring constant, and r is the internuclear distance. And in this case, the energy curve that we have, that energy is parabolic in nature, and if I assume that energy to be E, that's going to be 1 by 2 k times r minus r equilibrium whole square. Now, this model of vibrating diatomic molecule has exactly the resemblance with the so-called simple harmonic oscillator model, and and we can look for an approximation here, and for starting to discuss the vibrating diatomic molecule, we choose this problem to be equivalent to this simple harmonic oscillator model. Now, if I if I if I if I try to to go for, say, this is chlorine, we are assuming this chlorine to be at rest, and we have hydrogen. Say this hydrogen can be it can be extended, and it can be I'll call this H2 position. Let me have double dash and single dash here. So what should I say here is that, I mean, uh, the zero of if I have to plot it, if I have to look for what's going on here, if I choose chlorine to be at rest and assume that the mass of the hydrogen is uh, uh, it's the mass of the hydrogen is extremely small in comparison to the mass of the chlorine. So the motion of the hydrogen can be treated. Uh, it's treated to be dynamical in nature, and chlorine is assumed to be at rest. Now, uh, this figure that I have tried here, it shows that if one atom of chlorine is considered to be at stationary, uh, or is assumed to be at r is equal to 0 uh, axis, the other one, that's hydrogen, will oscillate, and this hydrogen will oscillate between H dash and H double dash. And in the case of this hydrogen chloride, I mean, it's a good approximation to say that during vibrations, this heavy chlorine atom virtually stays at rest, and it's for the much lighter hydrogen atom that's supposed to move, that's supposed to oscillate. And however, only the distance between the two atoms that we have here is important. And for any diatomic molecule, we can always imagine ourselves to be sitting on the atom, and watching the other hydrogen moving with respect to us. So from our point of view, the atoms, we are on its stationary, and can be assumed to be fixed at r equal to 0 axis. And if the energy of this HCl molecule, so here we have some energy, say this energy is epsilon 1. Now, if we increase the energy of this system from epsilon 1, and it's increased to some epsilon 2, so we have the same molecule, and we have hydrogen, and we have hydrogen. This is a single hydrogen that's compressed and extended with respect to the external force. So what can we say here is that when we increase the energy of this system, the oscillations will become more vigorous. So if I assume the energy E2 being greater than that of E1, so uh, so we will have a vigorous kind of situation here. That's to say that the degree of compression and extension will be greater in this case. But the vibrational frequency, if we go back to the classical understanding of the problem of spring, the vibrational frequency for both the states will not change. I mean, an elastic bond, like a spring, has certain intrinsic vibrational frequency. So this frequency is dependent on the mass of the system and the force constant. But but is independent of the amount of distortion. So here we have more distortion, and here we have less distortion. But this frequency is not dependent. The intrinsic frequency of the system is not dependent on this distortion. And if we think classically, it is simple to show that the oscillation frequency that we have, what is that? That is, if I take that omega, that is 1 by 2 pi under root of k by, if we choose here mu hertz. So this is the frequency, and we can see that this frequency is independent of the distortion that we have brought by adding the energy to this molecule. And this mu is the reduced mass of the system, and we can convert this frequency to the wave numbers. And the unit most usually employed in vibrational spectroscopy. So what we can do for that is we can divide this term by C, and if we divide this term by C, we will get the wave number. So wave number will be 1 by 2 pi c under root of k by mu. So instead of hertz, it will be centimeter inverse. And vibrational energies, like all other molecular energies, are quantized. And allowed vibrational energies for any particular system, they may be calculated by solving Schrodinger's wave equation. And we have the solution. We solve Schrodinger's wave equation for simple harmonic oscillator. And the equation that turns out to be is E, let me take nu here, is equal to nu plus 1 by 2 h cross omega. And let me call it joules. And this nu can have values 0, 1, 2, and so on and so forth. And this nu is called vibrational quantum number. So it's called vibrational quantum number. And we can convert this equation to the spectroscopic units by dividing this equation by hc, and we can write in terms of nu bar equal to E nu by hc. So what will be that? That will give us nu plus half and omega centimeter inverse. And so what we see here from these two equations is that the only energies that are allowed to simple harmonic vibrator and in particular, if we look at these two equations, we are able to notice down the lowest vibrational energy obtained by putting nu equal to 0 for both the cases. So if I write down if I write down this E nu and nu bar for the lowest vibrational energy, so I'll have E naught equal to 1 by 2 h omega, and nu bar equal to 1 by 2 omega. So here we will have centimeter inverse, and here we will have joules. So the implication is that that the diatomic molecule, and indeed, I mean, any molecule can never have zero vibrational energy, and the atoms can never be completely at rest relative to each other. So the quantity that we have, 1 by 2 h omega joules, or you may call 1 by 2 omega centimeter inverse, we call this thing as 0 point energy. 0 point energy. And it depends only on the classical vibrational frequency. So what we can say here is that the strength of the chemical bond and the atomic masses, the energy that's this 0 point energy. So the prediction of this 0 point energy is the basic difference, basically, between the wave mechanical model and the classical approaches. to the molecular vibrations. Now, what classical mechanics talks about it? Classical mechanics could find no objection to a molecule possessing no vibrational energy. But wave mechanics insists here. It lays a strong emphasis that it must always vibrate to some extent, and uh, and and the predictions of the wave mechanics are certainly found out to be the outcomes of the experiments. Now, furthermore, the use of Schrodinger's equation lead to a simple selection rule for this harmonic oscillator undergoing vibrations. And the selection rule is this delta nu is plus minus 1.